Hello, this is Coach Weidenbauer, and we're going to go over trig limits for calculus A, B, and BC. So a couple of special limits that we do need to be aware of are these limits as x approaches 0 of sine of x over x. If you do plug in a 0, you'll be in the form of 0 over 0, which means that we actually have a hole at 0. So this special limit says that is actually equal to 1. Okay, and since this ratio is equal to 1, we can actually manipulate it a little bit. That is the same thing. It's the same as the limit as x approaches 0 of x over sine of x equals 1. So the reciprocal is also equal to 1 because the reciprocal of 1 is 1. Also, please take note that as long as the argument inside of the sine function matches whatever is on the denominator or the numerator, that is also 1. So we can also write that the limit as x approaches 0 of sine of 2x over 2x is also equal to 1 because the argument for sine of 2x, of the sine function is 2x, and the denominator is also 2x, so that's going to equal 1. Now, for the cosine, we're going to get 0. Again, if you plug in 0 here, you're going to get 0 over 0. So this is going to be a hole. This is a special limit, and we're going to get a hole actually at 0. This one does not have a reciprocal because 0 does not have a reciprocal. So this one's pretty strict, where it's just 1 minus cosine all over x is equal to 0. So let's go down to these problems right here, and let's go ahead and tackle them. I have tangent of x over x, so let's find the limit as x approaches 0 of that. And what we want to do here is, big hint, is just rewrite tangents or anything else into sine over cosine so that we can utilize these special limits. So I'm going to rewrite this as the limit as x approaches 0, and tangent, if you remember, is sine over cosine. So it's sine of x over cosine of x. This is all over x, technically over 1. So I have a fraction dividing a fraction here. And what I'm going to do is I'm going to multiply by the reciprocal of the denominator. So this is the same thing as the limit as x approaches 0 of sine of x over cosine of x times 1 over x, because I'm multiplying by the reciprocal of the denominator. And all I have to do at this point is just do a little bit of rearranging. And I'm going to get the limit as x approaches 0 of sine of x over x times 1 over cosine x. After I rearrange that, you can see that sine of x over x is there, and we know that it is equal to 1. If I plug in a 0 into 1 over cosine, I'm going to get 1 over 1, so that's also going to equal 1. So I'm going to get 1 times 1, which is equal to 1. Let's go ahead and move on to the next problem. So now I have limit as x approaches 0 of sine 3x all over sine 5x. Now I'm going to need to manipulate this so that I have a 3x in the denominator and I need a 5x in the numerator. So I'm actually going to multiply this. So I have a 3x on the bottom. That will help me manipulate and move things around where I want them to be. In order for this to balance out, I have to have a 3x on top. I also want a 5x on top, so that balances with the sine 5x. So I need a 5x on the bottom. So this is everything that I need, and all I'm going to do is just rearrange everything very nicely. So I'm going to end up getting sine of 3x over 3x. So I'm using that times 5x over sine of 5x. So get that. And I'm left with not equals. It should be a times sign. It's an oopsie. 3x over 5x. So now I have a couple special limits here. I have this sine 3x over 3x, which is 1. 5x over sine 5x, which is also 1, because the argument matches the numerator. And really, 3x over 5x, those x's cancel out, and I'm left with 3/5. So this final answer would be 3/5. There we go. Let's go on to another one. This may or may not be on your notes. If it's not on your note, just go ahead and add this problem on here. So we have the limit as x approaches pi over 4 of 1 minus tangent x all over sine x minus cosine. If I were to plug in the pi over 4, the numerator would become 0. The denominator would also become 0. So I'm going to need to manipulate this a little bit. As I mentioned before, if we just change the tangent to sine over cosine, we can use some trig properties to rewrite this ratio. So I'm going to rewrite this tangent as sine of x over cosine x. Okay. And in order to do this, if I have 1 minus sine x, I'm going to do a little bit of side work here. Do that in purple. If I have 1 minus sine x over cosine x, I can rewrite the 1 as sine x. Oopsies. That's another oopsies for me. That should be cosine. So I get matching. I want to match my denominators. Cosine x over cosine x minus sine x over cosine x. Okay. So I'm now going to rewrite this limit as the limit as x approaches pi over 4 of now cosine x minus sine x, and that is all over cosine. So I just rewrote that numerator, 1 minus tangent. It's the same thing as my numerator right there in red, all over sine x minus cosine x. Technically, this is all over 1. So since I am dividing a fraction, I'm going to multiply by the reciprocal. So this is equivalent to the limit as x goes to pi over 4 of cosine x minus sine x all over cosine x times 1 over sine x minus cosine x. Now, the cosine x minus sine x, they're just opposite signs, so those do cancel out, but I have to make sure that I leave a negative 1 there. So it's going to leave me with the limit as x approaches pi over 4 of negative 1 on top now because of those were opposite signs. And now I'm free to go ahead and plug in my pi over 4. By the way, that is equivalent to negative secant of x. When I do plug in pi over 4, I'm going to end up with a negative 1 over root 2 over 2, which actually is equivalent to negative root 2. Okay. Oh, you just get 2 over root 2, which reduces down to just root 2. Okay. The very last thing here is, I think my picture is going to kind of get in the way here. The greatest integer function does show up on the worksheet that we do have, so please take note of that. The notation in the worksheet, you can just see it right there, is the brackets. I wish it was different. You can always use Desmos if you want to look at those problems. Feel free on those problems inside the worksheet that have that greatest integer function. And you can use the notation of floor x. So if it's the greatest integer of x minus 4, you would just type in floor x minus 4. You can also do the same thing in the TI-84. It's an int button. You can find the int of x using the math button. But anyway, the greatest integer function is always rounds down. So like 3.1 becomes 3, 3.9 becomes 3. Be careful when you get into the negatives because it actually goes down. So negative at 3.1 becomes negative 4. So that is what the greatest integer function is, but you can practice using it using your calculator. And that is going to wrap up our notes for today.